Hello guys, today I am here back to give a presentation on numerical simulation of flow past a square cylinder. Now I will give a small introduction on myself. I am G Sainareddy, having a pin number of 21955A2109 and my topic is numerical simulation of flow past a square cylinder. Abstract of this presentation. 2D and 3D unsteady flow past a rigid prism of square cross section with one side facing the oncoming flow is numerically simulated for Reynolds number between 200 to 500. An incompressible code is used employing an implicit fraction step meter, infinite volume with second order accuracy in space and time. For 2D flow, it is found that for Reynolds number greater than 300, the time mean flow pattern are not perfectly symmetric with respect to the oncoming flow. In contrast, such as non-symmetric mean flow pattern is not observed in 3D simulations. There is a marked and characteristic pulsation in the force components in the 3D flow for Reynolds number less than 300. This force pulsation contains characteristic time period with high and low level of forces. It is found that when the flow is within a low level of forces, the intensity of three-dimensional effects becomes stronger, whereas the opposite is true within a high level of forces. Now let us discuss about the introduction. In the past, the flow along bluff bodies such as circular and rectangular cylinders has been extensively studied owing to its relevance to technical problems associated with energy conversions and structural design. Over the last 20 years, a vast amount of studies has been conducted to increase the understanding of different transition process of the flow past a circular cylinder. By contrast, there are very few similar studies found on flow path rectangular cylindrical structure. Example, the square cylinder at moderate Reynolds number where a 2D or 3D wake transition occurs. As an example, at Reynolds number less than about 500, there is only a single set of experiments reporting the influence of Reynolds number on the mean drag coefficient. The main objectives of this present study were further investigate 3D transitional features in the flow past a square cylinder and to make additional comparison with 2D results at moderate Reynolds number, that is our Reynolds number is equal to 200 to 500. Now let us discuss about computational details. Let us observe the figure in which it shows about the flow configuration. The flow is described in a Cartesian coordinate system XYZ in which the x-axis is aligned with the inlet flow direction. The z-axis is parallel with the cylindrical axis and the y-axis is perpendicular to both directions as shown in figure 1. A fixed two-dimensional square cylinder with a side D is exposed to a constant free stream velocity, that is u infinite. An incompressible flow with constant fluid properties assume the Reynolds number is defined as Reynolds number is equal to u infinite into d by v. The following boundary conditions were used. A uniform flow was prescribed at the inlet, which is located xu units upstream of the cylinder, at the outlet location located xd units downstream of the cylinder. The convective boundary conditions were used for all velocity components. No slip conditions were prescribed at the body surface. Symmetric conditions simulating a frictionless wall were used at the upper and lower boundaries. A periodic boundary conditions was used in the span-wise direction. The normal derivative for the pressure was set to 0 at all boundary. In the present study, XU, XD and H were set to 8.5, 12.5 and 18 respectively. Now let us discuss about the wake flow transition. So on call. reports that the 2D results for mean drag are in reasonable agreement with experiments. All true other quantities for Reynolds number greater than or equal to 200 are for the most part in sharp contrast with available experimental data and the 3D results. Here we try to make additional comparison by comparing 2D and 3D flow characteristics. Within the early stages of the wake transition process, a marked and characteristic pulsation occurs in the flow components. See Soankar book. Now, such a pulsation is seen in figure 2 for Reynolds number is equal to Reynolds number 200, but it is not observed for Reynolds number 500. This forces pulsation contain characteristics time period with high and low level of forces, which are referred to as HF and LF region respectively. Here we try to expand this matter further by studying the vortex structure in HF and LF region. To study the main feature of the flow in these two regions, span-wise vorticity counters in the mid plane, at the instance of minimum lift force of Reynolds number 250 are shown in figure 3. Now let us observe figure 2, in which it describes about the time history of span-wise averaged lift and drag coefficient, in which the x-axis is considered as coefficient of drag and y-axis is considered as coefficient of lift. And next let us observe the figure 3, in which it describes span-wise vorticity counters in the plane z is equal to 0 in the position of minimum lift force. In the above figure and the other figure not shown there, it is observed that the shear layer developing from the upstream edges of the cylinder are not exactly similar in HF and LF region. In the LF region, the free shear layer from the upper edge are extended further downstream in comparison to a case in the HF region before rolling up to span-wise vortices. In addition, in the HF region, the free shear layers from the lower edge are rolled up closer to the cylinder than it is the case in the LF region. Thus, in the HF region, the first vortex is set in the wake at the position closer to the body. This is also consistent with the fact that the frequency of vortex settles is higher in the HF region than the HF-LF region. It is important to mention that the corresponding value of peak vorticity omega and pressure coefficient minus Cp at the center of the first detached flow in LF region are higher than in HF region. This means that the more intensive vortices are generated in LF region than in HF region. In general, the level of span-wise vorticity in HF and LF region is approximately similar. Example, consider the figure 4. In figure 4, it describes span circulation in plane together with span-wise average lift coefficient, span-wise vorticity and vorticity ratio. The circulation is calculated in the domain in general referring to figure 3 to 4, table 1, and as well as the other findings not repeated here. It is concluded when the flow is in a LF region, the intensity of three-dimensional effects becomes stronger, while the opposite is true in the HF region. Let us observe the table 1, in which it describes a summary of a result taken from span-wise vorticity counters at minimum lift instances. The ratio of span-wise vorticity and magnitude velocity and pressure coefficient are chosen at the point where vorticity is extreme. Now let us discuss about comparison between 2D and 3D. Sankar reported that 2D results of mean drag are in reasonable agreement with experiments. Also, other quantities for Reynolds number greater than or equal to 200, or for the most spots in short constraints with available experiment data and the 3D results. Here we try to make additionally comparison by comparing 2D and 3D for 3D flow characteristics. Time average streamline of 2D simulation of Reynolds number 300 and Reynolds number 500, and 3D simulation for Reynolds number is 500 as shown in figure 5. It is found that the time mean flow patterns are perfectly symmetric for Reynolds number less than or equal to 300, whereas the flow patterns were not perfectly symmetrical with respect to oncoming flow for Reynolds number 400 and 500. This non-symmetrical mean flow pattern in 2D simulation is shown in figure 5 for Reynolds number 500. As it observed in figure 5, the mean flow pattern for 2D and 3D simulation at Reynolds number 500 is approximately similar on the front, top and bottom sides of the cylinder, whereas there are many differences on the rear side where the wake flow develops. Let us observe the figure 5, in which it describes about the time average streamline in 2D simulation for Reynolds number 300 and Reynolds number 500, and a 3D simulation for Reynolds number 500. This differences is also clearly shown in figure 6, which shows the pressure coefficient around the cylinder. On the basis of this figure, the difference in Cp for 2D and 3D simulation is smaller on the sides of the body than on the rear. In spite of the differences in values of Cp on the rear side, the average value of Cp for 2D simulation on this side were the same as for 3D simulation. This is the reason why the drag coefficient for Reynolds number 500 is in good agreement in 2D and 3D simulation. It is the figure 6 in which it describes about the comparison of 2D and 3D results for Reynolds number 500. Time average pressure coefficient around the cylinder, time average pressure coefficient and streamline velocity of the center line. Conclusion: numerical simulation of unsteady 2D and 3D flow around the square cylinder at zero incidence are presented for Reynolds number 200 to 500. For 2D flow, it is found that Reynolds number is greater than 300. The time mean flow patterns are not perfectly symmetric with respect to the oncoming flow. In contrast, a symmetric flow pattern is observed in 3D simulation. It is believed that the symmetrical behavior in 2D simulation for Reynolds number greater than 300 in some way is related to the scenario of period doubling. The phenomenon of period doubling is a dominant feature in the 2D simulation, while there are no signs of such period doubling in the 3D simulation. Thus, it is expected that using 2D simulation of inertia 3D flow leads to a non-accurate prediction of flow structure and global quantity, because the structure of the flow in the spanwise direction is completely eliminated. There is a marked and characteristic pulsation in the flow components of three-dimensional flow of Reynolds number less than 300. This forces pulsation contains characteristic time period with HF and low level of forces. The central parts of the von Karman vortices at instant just after they have been detached from the cylinder appears to be more intensive in the low level of forces region than the high level of forces region. The intensity in this constant is based on the magnitude of the vorticity vector and the degree of pressure suction. The level of non-span wise vorticity is higher when the flow is in LF region, while the level of span-wise vorticity in HF and LF region is approximately similar. Thus, it is concluded that the degree of two-dimensional is higher in HF region, while the opposite is true in LF region. Thank you.